When you gaze at the night sky, you are looking backward through time. It comes down to a simple speed limit. Light takes time to travel. If the sun suddenly vanished right now, we wouldn't know about it for 8 minutes because the last rays of light would still be in transit. When we look at the sun, we see it exactly as it was 8 minutes ago. Scale that logic up across the cosmos. If you could instantly teleport to a planet 100 million light-years away and build a giant telescope to look back at Earth, you wouldn't see human civilization. The light reaching your lens would be 100 million years old. You would actually be watching dinosaurs. Because of this cosmic delay, space telescopes function as literal time machines designed to capture ancient history. The ultimate goal for astronomers has been to push that timeline back. They wanted to see 13 billion years into the past, to witness the exact moment the very first stars formed, 0.3 billion years after the Big Bang. Our previous greatest eye in the sky, the Hubble Space Telescope, couldn't look back that far. It maxed out around the 1 billion year mark. Because the universe is expanding, ancient light traveling toward Earth stretches. The space elongates, and the light wave elongates with it. This is redshift. The wavelength gets stretched so thin it drops out of the visible spectrum, shifting past red into invisible infrared. To see the absolute beginning of time, engineers had to build a machine capable of seeing invisible light. Infrared light is inextricably linked to heat. Anything with a temperature, from a human body to a sun-drenched satellite, emits this radiation. This creates a significant engineering challenge. Because the telescope itself generates heat to operate, its own electronics glow with infrared light. If that internal heat isn't neutralized, the machine's own radiation will overwhelm the faint signals coming from the deep past. To solve this, engineers first built an enormous catcher, a mirror wide enough to gather as much of that incredibly faint ancient light as possible. They constructed a honeycomb-like array of mirrors, plated entirely in 24-karat gold. Gold happens to be the absolute best material in the world for reflecting redshifted infrared light. Gathering that ancient light was only the first step. The true impossible task was ensuring this colossal instrument remained completely devoid of heat. This top-down orbital map shows the Earth, the Sun, and a specific spot 1.5 million kilometers away known as the L2 Lagrange point. You couldn't park this machine right next to the Earth like we did with Hubble. At L2, the Earth constantly blocks the Sun's direct path to the telescope as they revolve together. But even deep in Earth's shadow, ambient solar heat in the vacuum of space is enough to fry the sensors. The telescope needed a massive physical barrier to block the residual thermal waves. Engineers designed a sunshield the size of a tennis court, shaped like a massive kite. It's built from 5 vacuum-separated layers of a specialized material called kapton. Every individual layer is thinner than a strand of human hair. This multi-layered umbrella successfully drops the operating temperature of the main mirror to a freezing minus 223 degrees Celsius, keeping the telescope from blinding itself. Maintaining that absolute cold required over 300 individual mechanical deployments. Every hinge, motor, and cable had to work perfectly on the first try. Because there is no way to send a repair crew to L2, a single failure in this $10 billion sequence would have rendered the entire mission useless. To get into deep space, this entire structure had to be folded up and strapped to a rocket. If a single piece of kapton snagged or tore during its deployment sequence 1 million miles from Earth, the entire mission was over. Humanity gambled a decade of work on perfectly choreographing remote mechanical origami in deep space, just to achieve absolute cold. The gamble paid off. The deployment was flawless, and the James Webb Space Telescope is now capturing the cosmos with a clarity we've never possessed. In the past, whenever we tried to observe distant stellar nurseries using visible light, thick clouds of space dust and gas trapped the light and blocked our view. This split-screen comparison shows exactly how the Webb overcomes this. On the left, thick, cloudy space dust in visible light. On the right, infrared sensors pass straight through, revealing high-definition images of stars forming directly behind the obstacles. This operational time machine is currently catching light that was emitted when the very first stars ignited, nearly 13.5 billion years ago. The telescope's precision is also being applied to the search for habitable worlds. This level of infrared clarity allows scientists to analyze the atmospheric makeup of distant, uncharted exoplanets. By observing the earliest moments of the universe, the James Webb Space Telescope is providing a blueprint for the future. Scientists are now using this infrared clarity to analyze the chemical signatures of distant, uncharted exoplanets, searching for the specific atmospheric markers that could signal the existence of another Earth.